Today we will use logistic regression modeling to predict if a student will receive an A grade, which is 80 plus marks, based on the behavioral patterns seen in this raw data. The first step is to dummy encode the raw data into binary values. We begin with age, encoding the 16 to 19 years range and leaving out 20 to 24 to avoid multicollinearity. Then we select male datas for gender, leaving out all the female datas. Then we divide gaming hours into low, moderate and high categories, where low is under 2.7 hours per day and high is over 5.7 hours per day. Study hours are divided into low, optimal and high categories, as research suggests the optimum time is 4 to 6 hours per day. We then encode sleeping hours into low and optimum, as 7 plus hours is the optimum sleep time for an individual. Attendance is divided into poor, below 65%, moderate and high, above 85%. Since gaming genres were already categorized, I will take FPS and RPG while leaving out the casual genre. Social activity is again divided into low, optimum and high categories, where low is under 1 hour per day and high is over 3 hours per day. As addiction scoring did not use a specific scale, we use 3 quartiles to denote low, moderate and high addiction scores. Stress levels were already categorized as low, medium and high, so we will only use the low and high values for dummy encoding. And finally, we encode the A grade as our dependent variable. After this, it's time to split the data into 80-20 ratio, for which I randomize the raw data and filter the ones and zeros in dummy encoded sheet and copy the required numbers to training and test set. In training set, we will use 1600 ones and 1600 zeros so that they are in 50-50 ratio, and in test set we use 240 ones and 560 zeros, which is 70-30 ratio, duplicating the ratio in raw data. Now we take the training set to find linear combination using the regression formula with all beta values as 1. Then we do the sigmoid transform formula, which is e to the power the linear combination value divided by 1 plus e to the power the linear combination value. Then it's time to find the maximum likelihood estimate by summing up all the log likelihood values in the probability column. Afterwards, we maximize the MLE value by changing the coefficient values using the solver function. Now that we have trained the model, it is time to test it. First, we find the logistic regression values using the regression formula again, but using the beta values optimized by the solver function. Then we calculate the probability once more using the sigmoid transform formula. To evaluate the performance of the model, we first find the minimum and maximum probabilities of the test data and create cutoff values at 0.01 intervals. Then we calculate the true positive rate, which is the percentage of A grades we correctly predicted out of all actual A grades. And the false positive rate is also calculated, which is the percentage of instances where we predicted an A grade even though the student did not achieve one. The ROC curve has now been charted using the true positive and false positive rates. We then move to finding the values for the confusion matrix using a cutoff value that looks favorable to us. Next, we calculate accuracy, which is the degree of correct predictions across the dataset. Precision, which reflects the model's reliability in predicting an A grade. And recall, which is the model's capability to identify students who actually achieved an A. We also calculate specificity, which measures the model's ability to correctly identify students who did not achieve an A grade. Then we calculated the F1 score, which provides the harmonic mean of precision and recall to balance the trade-off between the two. This is especially useful when there is an uneven distribution of classes. Our target is to maximize this score, so we run the solver to do so by adjusting the cutoff value. Using this final cutoff, we calculate negative predictive value, which is the probability that a student predicted not to get an A grade actually did not get one. The false positive rate, which is the proportion of students who did not get an A but were incorrectly predicted to achieve one. The false negative rate, the proportion of students who actually achieved an A but were missed by the model. Balanced accuracy, which is the average of sensitivity and specificity, providing a fair performance metric since our test set classes are imbalanced. Positive likelihood ratio, which is how much the odds of a student getting an A increase given a positive prediction. And negative likelihood ratio, which is how much the odds of a student getting an A decreases given a negative prediction. We also calculate the area under the curve for the ROC curve by using the trapezoid formula for each cutoff interval, then summing those values to find the total area. Here I added a short interpretation of my model coefficients and the reasoning behind the cutoff decision. Thank you for watching the video.